here's the plan for today. I've uploaded a second exam onto Google Classroom. This has to do with how the class was set up last year. Last year I had 5 tests scheduled. I had the chapters were set up differently, so we're going to jump around. Test 1 was over chapters 1 and 2. So there is a emphasis on that material, so there's a lot more focus on density, a lot more focus on finding the melting point, the conversion of temperatures. There's not as much of that on the test for this year because I'm covering chapters 1, 2, and 3. Now on the test 2, which we'll start looking at today, they go over chapters 3 and what was chapter 4 last year, but this is going to be chapter chapter 8. So it would be like chapter 3 and chapter 8. So some of that stuff on test 2, which we're going to look at, is not going to be applicable right away. It'll come back around when we get to stoichiometry chapter, but I'm going to skip over those problems. So with that in mind, we'll go ahead and get started. And I'll be switching between this and the board work. But so, okay. Is this Max Mouse? Yeah, it is. Oh, yep. Okay. We had just finished problem 4. Oh no, we just finished whatever the first page was. I think it was problem 4. So problem 5 right here, where we'll start. Problem 5, it's a silly problem, and it's a problem with an equation I don't expect you to have known or ever have seen before. But with that in mind, if you understand dimensional analysis, you can figure this out. If you do not understand dimensional analysis and you're still struggling, do feel free to contact me. The only real contact I've had with students have been more or less from nursing students or when I see you guys in lab. I've been playing email tag with many of you, but feel free if we need to work through some problems together. I will be glad to take the time. Just got to let me know and we'll set up a time. But okay, let's read through the problem. The average wing velocity of a European swallow is 15 beats per second. Each beat allows a swallow to move 0.73 meters per beat. What would the airspeed velocity of an unladen swallow be in miles per hour? So the underlying problem is we want to convert. Oh, sure, not that. No, not that. Okay, we want to convert meters per second into miles an hour is the underlying problem. But first, we have to get it in meters per second. I'm setting up the first equation part for 15 beats per second. No, we're not used to seeing beats as a unit, but that's okay. And we are going to use the meters per beat to get this into a meters per second. So am I going to multiply? Am I going to divide? Well, that's where dimensional analysis will help us because the dimensional analysis says if I want meters per second, I need beats to cancel out and I need meters to be on top. So if I move 0.73 meters per beat, wing beat, beat, and beat will cancel out. We'll be left with only units of meters and only units of seconds. So quickly doing this math, how far will swallow move in 1 second, assuming average wing speed. You move 10.95 meters in a second. Okay, 10.95 meters. Now, the way I gave them all the information to do this would have had to be like this. They would have had to go meters to centimeters. So 1 meter is 100 centimeters. Then they'd go, they're 2.54 centimeters in 1 inch, 12 inches in 1 foot, and 5,280 feet in 1 mile. There is a shortcut. If you know the shortcut, you can do the shortcut. But I didn't give them the conversion for the shortcut. So since we're doing an online test, if you have extra conversion data, you're more than welcome to try to use it. But do actually learn how to do this. Don't just try to Google it. So the other way is you could go 10.95 meters and say, there is 1,000 meters in 1 kilometer. And there is approximately, in 1 kilometer, there's approximately 0.62 something miles. I don't know this conversion right off the top of my head. But if I do those numbers, do those conversions, multiply by everything on top, divide by everything on bottom, we get approximately the same number in in miles per second. I'm going to do the top one just to save a little bit of time. And I get something like 0.006789 for the top one. I think if you do it properly, it's like 0.0068 something. It doesn't really matter. The next step would be we have to convert this into miles per hour. We got it in miles because meters cancel meters, kilometers cancel kilometers. So we're in miles per second. Next step is there are 60 seconds in a minute, 60 minutes in an hour. Minutes cancel minutes, seconds cancel seconds. We are left with miles, hours. So take our value, multiply by 60 and 60 again. You get the average bird speed is 24 miles an hour. So that would be answer B, 2.4 times 10 to the first. You'll notice all of them are in scientific. That is because I didn't want to make it so obvious of the different possibilities. The tricky part, all of these possibilities are possibilities you could get if you screwed up your math horribly. But taking a look at some of those answers, you'll see really there's only 1, maybe 2 possibilities. Let's look at those answers real quick. We have 1.2 times 10 to the 8th. Let's think about it. That's like 120 million miles an hour. I don't think we have a supersonic cheetah bird here. So that one's right out. And 8.4 times 10 to the negative 9th. It'd be like measuring a slug traveling. If even that. It might even be smaller than a slug. Be like when we try to calculate how long it takes the earthworms to move up into Canada from like Mexico. Yeah. So the only ones that even make sense would be like B or D. So if you can look at the answers and say, oh, that's way unreasonable, hopefully you can say, if somehow you got A, you like did a conversion wrong and you got A, you'll be like, well, you won't be like, well, that's what I got. Obviously, the bird's moving close to the speed of light. Like you won't be like, oh, be like, wait, I must have done something wrong. You can look at that and go, okay, moving on. Lab tech weight. This is because this was just chapter 1 and 2, I had a lot of lab-based stuff, lab-based questions. So don't worry so much about this, but how would you determine the average and standard deviation? You took 9.13, 9.25, 9.32. So remember an average. You add them all up and you divide by 3. Add them all up and divide by 3 to get the average. To get the standard deviation, 1.3, so 9.2 and 9.32. The average is 9.23. To get the standard deviation, oh crap, do I know? All my markers are over there. Well, that sucks. Oh, this sucks. Standard deviation, we take the difference between the two. 9.23 minus 9.13. Difference of 0.1. 9.25 minus 9.23. Difference of 0.02. 9.32 minus 9.23. Difference of 0.09. We sum them up. We sum them up and we take the average. That's how you calculate the standard deviation. The difference from each value from the average is how you calculate the standard deviation. You had a question?
Okay, so all of those added up and divided by 3. What?
9.23. So, and I'm taking. Okay, so you're always taking the absolute value of the difference. So I don't want a negative 10, I want a positive 10. So it doesn't matter whether I'm subtracting that from that or that from that. I always want the positive value. So I sum those up. You'd get the sum of all those differences is 21. 21 divided by 3 is 0.07. So my average is 9.23 with a standard deviation of 0.07. Okay. I'm not going to go through all this test, but I'm going to go through at least enough that you will see all the types of problems. This is a classic one that's something easily done on the test. If it marks you wrong and you think you're right, don't worry. I'm going to review all the answers on the test. So even if I didn't predict what crazy response you would put in, you accidentally put in an extra space or something, if you still have the right answer, just not the right format, I'll find a way to mark it right. But okay, so we are going to calculate the proton, neutron, electron count based on the atomic number, mass number, and charge. I don't know why the number 24 and whatnot. I'm not sure what that is. I'm not going to worry about it. But I'm not sure what that number's there. I don't know what goofed up. I'm not going to worry about it. But so, okay, hydrogen, the atomic number is 1. The atomic number is directly related to the proton count. And so, and the proton count is direct and atomic number both define the element. So because of that, hydrogen has 1 proton. The mass number, let's see, the mass number is equal to the protons plus the neutrons. So with a mass number of 3 and a proton count of 1, we must have 2 neutrons. And the charge, I'm going to put it as a Q, charge is equal to the protons minus the electrons. The charge is -1. So 1 minus what number would give us -1? 1 minus 2. So we'd have 2 electrons. So the correct answer for hydrogen is H. It would be 1, 2, 2. You cannot simply look that up on a periodic table because proton's most common isotope would be 1, 0, 0. You have to be able to do that. You can't just Google this. Some of them you might be able to Google, but if you get lucky. But 10, 50. So 50, you could get the proton count just fine. 50 is the protons. 116 is the mass number. So 116 minus 50 is going to be 66 neutrons. And 50 minus X is equal to 4. So the electrons must be 46. Feel free to, you can do this on a calculator. You don't have to do this in your head just because I'm doing it in my head. I'm trying to save a few seconds. 8, we won't really have to worry so much about 8, but 8 was, we're trying to image what exactly what type of mixture. This was essentially a circle filled with X's and black circles, and the black circles were mixed throughout it. It was mostly gray X'd things. If you look at the actual thing, you can see the full circle. But basically, it's not a pure element. It's not a compound. These are not bound together. They're mixed together. So the question was whether it was homogeneous or heterogeneous. And the idea was heterogeneous should have been, say, like all the black ones would be on one side and all the X's on the other side, as opposed to what we have in the circle where it's like X, 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 dot, dot, dot. The dots are kind of interspersed. But I'm not going to ask that. Once again, when I'm dealing with 20 questions from only 2 chapters, I'm kind of limited on the material, and so I'm going to hit all the things, including definitions, extra hard. But I'm not really focused nearly as much on definitions. Now, this one, question 9, feel free to study the experiments we talked about at the beginning of chapter 2, though. I will ask at least one question about the experiments, like maybe the cathode ray tube, maybe the milk and oil drop, maybe Rutherford gold foil experiment. Just be semi-familiar with what went on and what it did. Like, what did this find out? Oh, the milk and oil drop found out the charge of the electron, and thus we could figure out the mass of the electron. Here's the Rutherford. he fired alpha particles at gold foil to test the permeability of the atom. What did he discover? Did he discover that the plum pudding model was incorrect? That the atom had a small dense nucleus? That the atom was largely empty, or all of the above? The correct answer is all of the above. So because the plum pudding model thought we had a dispersed positively charged atom, and instead we have a densely concentrated nuclear center, positively charged nuclear center, with most of it being empty. This one was just give an example of a chemical physical change. Rather than me think of something, I threw something out for people to be creative. Remember, physical changes do not change it could change how it looks, but not any of the chemical properties. I could melt something, I could boil something, but if I'm melting it, even though, like, yes, water is less dense as less dense as ice, and it's or less dense as steam, I can put it right back by letting it condense again. Oh, mixing two things together, like dissolving salt crystals. Yes, the technically they do split apart and they're no longer like a solid, but I can recrystallize it back out. It's not a permanent change. If I crush a boulder, that's yes, the boulder is. I can't uncrush a boulder, but the boulder is whatever rock it's made up of. I'm not changing the property of the rock. I'm just splitting it into smaller and smaller subdivisions of the same atoms. A chemical change is more of a permanent one, like burning something, allowing something to rust, allowing something to react in one way or another. And breaking chemical bonds down. Let's see. This one is just another density problem. I'm going to go ahead and give this one. I'm going to have to change how we look at this because otherwise we won't be able to see this. Okay. Okay, well, I'll look at that, yeah. So the Archimedes Principle, essentially, you can tell the density of object, the purity of object by its density. And if you had a crown that weighed 235 grams and displaced 15.32 mils, what would be its density? And is this pure gold? So this was a fill in the blank one. Wasn't too hard. You had to check the sig figs, but 4 sig fig value divided by a 4 sig fig value, you should have an answer that's 4 sig figs. And then you had to just make sure you answered the second part of the question, which is this actually gold? Sorry. I'm kind of locked in place. I hate when both erasers are over there, but that's what I got. So, looking at this. But to get density, mass divided by volume. So 235.6 grams divided by 15.32 mils would give us our density. Doing that conversion, let's see, 235.6. I get 15.37. So, someone's in trouble. 15.38. Sorry, 15.38. So that crown is not pure gold. It should be pretty close. Should be pretty darn close in order to. The original story of Archimedes was that, like, the king gave the blacksmith or the goldsmith pure gold to make his crown. And the goldsmith supposedly maybe mixed with some lesser metals, make it weigh the exact same, the exact same as the amount of gold given, but was able to stretch the gold further in such a way that it looks like the same, but he kept some of the gold for himself. The king suspected treachery and brought Archimedes. Say, is there a way to find out, is this pure gold or have I been cheated? And he stepped into it. He was thinking about this, pondering it, and the Grecian baths, and he stepped into a bath and the water flowed over the sides when he got in, and he had an idea, and he went shouting down the streets naked, "Eureka, Eureka," which means I found it, I got it. And so using water displacement, he was able to determine the density of crown and say, oh, no, that's not pure gold. Though there is maybe a little bit more complication to the story of how he actually did it. Well, it's not so simple as what we did with what we did in lab, but there is still a way using the same general principles. Yes. Yeah, well, you could coat it. You could coat it. You wouldn't actually be turning it into gold, but yes, you could coat it. We have done some things where we've turned essentially a glass beaker or glass Erlenmeyer into silver by essentially reducing silver onto the glass, and that's actually how they coated the surfaces of glass mirrors, that essentially back them with silver so that they reflect the light of the glass pane, which is part of why mirrors were so expensive back then, using like silver backing. Well, okay, this one, look for something like this. Okay, I got to bring this over here so you can see it. But report this value to the correct number of significant figures. So it may not be a Erlenmeyer flask, maybe it'll be a ruler, but the idea here is, what is this to the correct number of significant figures? The rule of this is you always record all the digits from the lines, but you always include an estimation point between the two marks. So you can see here that this is between the 4 and the 5 for clearly. Everyone should get this as 4 something. Then you want to read the meniscus, which is the bottom of the bubble, which is right here. Sorry, I need to get this on the right screen. Right here. And so that's between the 2 and the 3. There's 4. So everyone should say it's 2, but for maximum credit, you would say, well, it's not exactly on the 2. So it's somewhere between 2 and 3. You might say that's 4.24, 4.26. That's really up to your eyesight. And there's several possible correct answers depending on what you determine it to be. There is more than one correct answer, but it has to be to that estimation point to be most accurate. And that's what I would be looking for on one like that. So you're taking it to the estimation point, not just, well, I can read it. Statement is false. Don't worry so much about the theories. Let's see. I'm trying to remember where I stopped. This is another temperature one. We can do this. I will go ahead and do it, but temperature is not going to be as big a part on the test, mainly because we have 3 chapters of material, and chapter 3 is pretty dense. But I'll go ahead and do this one. So you need, just because it shows us using an equation. So the temperature of the sun is 5,778 Kelvin. And mind you, this is the surface of the sun. It gets hotter as you get closer to the core. So 5,778. Well, I gave them 2 equations. Celsius plus 273 equals Kelvin. And I gave them Celsius times 9 over 5 plus 32 equals Fahrenheit. So you always go through Celsius just like we always go through moles. So to go from Kelvin to Celsius, we are going to subtract 273. So that's going to give us our temperature of the sun, or the surface, is 5,505 Celsius. And then we're going to have 5,505 times 9 divided by 5 plus 32. That's 1101 times, so you get 9909 plus 32. So you get 9941. So answer C. But thing of it is, doing this in an improper order could get you most of those possibilities. Thank you. So doing those in an improper order could give you most of those possibilities. Okay. Don't know what that. Okay. This one, we will do these last 2 or 3. Well, we'll do 15 and 16, and then we'll stop this one and start looking at the last one. So this one's going backwards. Using the given proton, neutron, and electron count, determine the chemical element, the atomic mass, and the mass number and the charge. So with just the proton count, we can look up where that is on the periodic table. So on the periodic table, the top number is the atomic number, and the bottom number is the average atomic mass, the weighted average. With proton count of 40, now don't think it was like, wow, how did you do that? I remember this from literally doing this yesterday. 40 happens to be zirconium. Zirconium. It's not magic. I just literally remember this from yesterday. Now, zirconium, I don't know what its average atomic mass is, but on this particular isotope, it's going to be 40 plus 50, so a mass of 90. And for the charge, 40 minus 38, so which gives us a positive 2. Correct answer would be either this, which I'm going to, either zirconium 92 plus, or you could leave in the 40. Either one would be acceptable. But the idea is that you have the mass number and the charge, and you have the element correct. The next one, proton count 35. Took me a minute, but I remember this one as well. That one happens to be bromine. Bromine. If that's 35 and the neutron count is 46, 35 plus 46 is 81. And you can't read it because it's cut off the screen, but where'd my mouse go? But the electron count went to the bottom, 36. 36, 35 minus 36 is -1. So the correct answer would have been bromine 81, -1, or 1 minus. Either one would have been acceptable. And we'll finish up with number 16 real quick. Okay. Scrolling down, this one was actually significantly easier than what we might see, because this one, that year, I did not really teach the math behind this. And this year, we actually had a couple problems on the homework. Now, it's not going to aim to be too hard, but you still have to figure this out. If the atomic weight is calculated based on the weighted average of all isotopes, which isotope of copper would you expect to be more abundant based on the average atomic weight of 63.5? So this is how you could think of this without actually doing any math. If we have copper 63 and copper 65, where's 63.5? 63.5 is right here. The four possibilities are 63 is more abundant. 63 is more abundant. Oh, where did this? 63 is more abundant. 65 is more abundant. Neither is more abundant, or more information is needed. Based on this, 63.5 is much closer to 63 than it is to 65. If this is a weighted average, 63 must be more abundant, because if they were equally abundant, we would have a mass around 64. How would you calculate this? You take the mass of 63 times its percent and add the mass of 65 times its percent, and that's how you got the 63.5. So there would be percent A and percent B. And what you'd find, oh, this would have to be, well, that's 75% and that's 25%, something like that. And that's how you would have got 63.5. That's how you would do the math. And with that in mind, I'm closing out this test. I'm not going to work on 17 and on. It's not worth the effort. Let's pull up this, toss it over here. Look at exam 2, and we're going to jump around. I'm going to skip this number 1. Number 1 is not of any use. We did not go over reducing agents. Down. This one is something more like what we need. Which of the following ion is considered sulfite? Which of the following ion? Well, oh shit, I gave the answer. What is the name of the following ion? So it is an ion. So the first thing to note is it is not sulfur oxide. It's not sulfur trioxide. Those would be naming these guys if we were talking about a compound. Sulfate and sulfite are names of the oxyanion. So then it becomes recognizing sulfate is SO4. SO4. So SO3 must be its smaller brother, sulfite. And one way to remember this, and this is stupid, but it might actually stick. 8, like I ate a lot, I'm all full, is always the bigger number. But ite, I just took a small little bite. So bite or ite is the smaller, the lesser of the two. Moving down, we are skipping number 2. We're actually going to skip number 3. We haven't done this in the lab, but empirical formula. Empirical formula being 3 and 4 are related. Okay. This one is actually, number 5 is maybe twice as hard as what you might see on the test. in that it combines two steps together. It combines, well, the mass in grams. It is saying, what is the mass in grams of this many atoms of lead? How much would that weigh? This combines the conversion of atoms to moles, and it combines the conversion of moles to grams. Now, I might ask you those two things separately. I'm not sure if I'm going to ask them together because I'm going to take it a little easy on the math coming into this. But we should be able to, with dimensional analysis, do this. So I'm not sure if this is going to look like. Yeah, that's going to cut out entirely. So I'm going to just switch back to this. We're going to work that out. You're just going to have to listen to my voice to see what the problem was. Yeah, it's okay. I don't. That's why, because I'm hitting the buttons. I'm hitting the buttons to switch between screens. That's where that's coming from. I figured it out. So this is atoms. As atoms. In order to turn atoms into moles, we use Avogadro's number. This doesn't matter what we're dealing with. There's always 6.02 times 10 to the 23rd atoms of anything in 1 mole. You can do this separately or in one step. You can do this separately in one step. If I remember right, lead is something like 207.2 grams per mole from the periodic table. But without looking, I can't directly remember. You can do this in 2 steps or 1 step. Doesn't really matter. But do know, pay attention. I divide big number by big number. Whatever your answer is, it should be a small number. So answer B should not be. Answer B is if you screwed up step 1 and you multiplied by 10 to the 23rd instead of divided. So when you do the first step, you should have got 5.84 moles. Or let's say 5.85 moles. 5.85 moles times 207.2 grams per mole means this is going to weigh a lot. It's going to weigh a lot. But then again, lead is really, really heavy. It's one of our densest metals we got. Really heavy. So almost 6 moles of this weighs about 1.2 kilograms or 1,210. So the answer is A, 1,210. Skipping this one. Skipping this one. Here we go, something we can do. Determine the chemical formulas. Be prepared to turn chemical formula into name or name into chemical formula. Son, we're going to be doing hydrobromic acid. The hydro tells us that it is just the anion without any oxygens attached. So hydrobromic, meaning it's just HBr. Nitrogen monoxide, well, that is NO1. So NO, just NO. It's the mono tells me it's a bimolecular. Nitrogen, because it's 1, doesn't need a prefix. scroll up instead of scrolling down. We will maybe finish with this one. I'm not sure how much, but I just want to look real quick. We can do 9. We can do 11. We can do 12. 12. And we can do like 16 and 17. 16, 17. And possibly 20. 16, 17, 20. So we'll see how much time how far we get. We'll finish this up on Friday, but just in case, I'm going to keep you a minute or two afterwards just to finish this one real quick. But just in case, I'm setting the test out tonight. You can access it on Thursday morning. But it doesn't have to be done till the end of Labor Day. It doesn't have to be done to the end of Labor Day. Once you get started, you have 2 hours to finish it. So you may want to wait till you know you have 2 hours available. So if you have a shift at work, make sure you plan your shift around that. Like, don't get started if you're like, oh, I got to go get ready in half an hour. So if 40%, 100 grams of xylose is burned to get 40% carbon, 53.3% oxygen, and 6.67% hydrogen by mass. What is the empirical formula? So just empirical formula. We have, it's 40%, 53.3, and that have to be 6.7. Now, the beauty of percent, especially when you're dealing with 100 grams, is those can be converted directly into grams. Do not pass go. Do not collect $200. Don't have to do anything. That's carbon. That's oxygen. That's hydrogen. I'm going to assume I'm going to be lazy. 1 gram per 1 mole. That's 6.7. This is 12 grams, 1 mole. Where am I pulling these? Periodic table. All from periodic table. So 40 divided by 12 is 3.3. And 53.3, that's 16 grams per 1 mole. So 53.3 divided by 16, 3.3. I divide by the lowest number, 3.3, 3.3, 3.3. What would I get? Carbon 1, hydrogen, well, that's about 2O1. Xylose has the same empirical formula as glucose, as formaldehyde. It is one of the common 5-membered sugars. The actual structure is C5H10O5, but 1 to 2 to 1. What do? Turn grams into moles, divide by the lowest number of moles to get a full ratio. That is what we must do. We'll maybe do one more of those later. That's where we're stopping for today. Have a good day.